Picture this: a distance so small, it defies comprehension. It's not just tiny, it's the smallest measurement we know of in the entire universe. This is the Planck length, a scale so minuscule, it's 100 million trillion times smaller than the width of a single atom. At this unimaginable level, the very fabric of space and time changes, bending the rules of reality as we understand them. It's here, at this frontier of human knowledge, that we find ourselves staring into the abyss of the unknown, a place where the familiar laws of physics break down and the mysteries of the cosmos begin to deepen. What lies beyond this infinitesimal distance? What secrets are hidden in the quantum shadows that lurk just beyond our reach? Quantum shadows, a term that evokes both intrigue and mystery. These are the phenomena that might exist beyond the Planck length, phenomena we can't yet see, measure, or fully understand. They're the whispers of a universe that operates on scales so small, they challenge our very perception of reality. Could these shadows hold the key to the universe's deepest mysteries? Could they reveal the hidden structure of space, time, and existence itself? As we stand on the precipice of this new frontier, we're forced to confront questions that push the boundaries of science, philosophy, and imagination. What if the answers we've been searching for, the nature of reality, the origins of the cosmos, the very essence of existence, are waiting just beyond the smallest known distance? In this video, we're going on a journey into the heart of the unknown. We'll explore cutting-edge theories that attempt to pierce the veil of the Planck length, diving into the realm of quantum shadows and the mind-bending possibilities they represent. We'll unravel the work of physicists who are daring to ask the biggest questions, and we'll examine the groundbreaking ideas that could redefine our understanding of the universe. Along the way, we'll uncover the incredible efforts being made to peer into this infinitesimal world, from advanced mathematics to the latest in experimental physics. This isn't just a story about science, it's a story about human curiosity, about our relentless drive to uncover the truths that lie hidden in the fabric of reality. So join me as we venture into the quantum shadows and ask the question that has captivated scientists and dreamers alike: what hides beyond the smallest known distance? The Planck length is more than just a number. It's a gateway to the very edge of human understanding. Named after Max Planck, the father of quantum theory, this tiny distance measures about 1.616 times 10 to the power of negative 35 meters. To put it into perspective, if you were to magnify an atom to the size of the observable universe, the Planck length would still be smaller than a single grain of sand on that cosmic scale. But why is this distance so significant? It's not just about size, it's about the fundamental laws of nature. The Planck length is derived from three universal constants: the speed of light, the gravitational constant, and Planck's constant. These are the building blocks of our physical reality, and when combined, they give us this smallest meaningful distance. At this scale, the rules of classical physics, the physics of everyday life, begin to crumble. Gravity, space, and time as we know them no longer behave in predictable ways. Instead, we enter the realm of quantum mechanics, where particles can exist in multiple states at once, and the fabric of reality becomes a swirling sea of probabilities. Beyond the Planck length, our current theories suggest that space and time might dissolve into something entirely different: a frothy, fluctuating quantum foam, or perhaps a network of fundamental strings vibrating at the heart of existence. This is where the idea of quantum shadows comes into play. These shadows could represent phenomena that exist beyond our ability to measure or observe, phenomena that might hold the answers to some of the most profound questions in physics. Think of it like this: if the universe were a canvas, the Planck length would be the smallest brushstroke we can see. But what lies beneath that stroke? Are there smaller patterns, hidden textures, or entirely new dimensions waiting to be discovered? The concept of quantum shadows suggests that there might be. They could be the echoes of parallel universes, the remnants of higher dimensions, or even the fingerprints of a deeper, more fundamental reality. While we can't yet peer beyond the Planck length, theories like string theory and loop quantum gravity offer tantalizing glimpses into what might be hiding there. These ideas push the boundaries of science, challenging us to rethink everything we thought we knew about the universe. As we continue to explore this uncharted territory, one thing is certain: the quantum shadows hold secrets that could change our understanding of reality forever. Quantum shadows are like whispers from a realm we can't yet see, tiny ripples in the fabric of reality that hint at something profound. These theoretical phenomena are thought to exist at scales even smaller than the Planck length, a distance so minuscule that our current tools and theories can't directly probe it. Imagine standing at the edge of a vast, dark ocean, hearing faint echoes from the waves beyond your sight. Quantum shadows could be those echoes, fluctuations, particles, or even entire dimensions that remain hidden from our instruments. They might represent the faint traces of a deeper layer of existence, one that operates under rules we've yet to uncover. What makes these shadows so fascinating is their potential to reshape our understanding of the universe. Some theories suggest they could be the remnants of higher dimensions, curling up and folding in ways that make them invisible to us. Others propose they might be the building blocks of space and time itself, flickering in and out of existence like the static on an old television screen. Picture a vast, intricate tapestry, the universe as we know it. Quantum shadows could be the threads we've yet to notice, weaving together the unseen patterns that hold it all together. Studying these shadows could unlock answers to some of the biggest questions in physics. For instance, what happens to gravity at such tiny scales? Why does the quantum world behave so differently from the classical one? And could these shadows be the key to uniting the forces of nature into a single, elegant framework? While we can't yet observe them directly, theories like string theory and loop quantum gravity offer pathways to explore these possibilities. By delving into the nature of quantum shadows, we might one day uncover the true essence of reality, a reality far stranger and more wondrous than anything we've imagined. String theory offers a tantalizing glimpse into the nature of quantum shadows by suggesting that our universe might be far more complex than it appears. At its core, string theory proposes that the fundamental building blocks of reality aren't particles but tiny, vibrating strings. These strings oscillate at different frequencies, giving rise to the particles and forces we observe. But here's where it gets fascinating: string theory also predicts the existence of extra dimensions, curled up so tightly that they're invisible to us. These hidden dimensions could be the playground for quantum shadows, fluctuations so minute they exist at scales smaller than the Planck length. Imagine a guitar string vibrating in a room. The notes it produces depend on how tightly it's stretched and how it's plucked. Now, think of the universe as a cosmic symphony with strings vibrating in multiple dimensions. Quantum shadows could be the faintest, most subtle notes in this symphony, resonating in dimensions we can't perceive. String theory suggests these shadows might not just be abstract ideas but real, physical phenomena that influence the fabric of reality in ways we're only beginning to understand. However, testing these ideas is no small feat. The scales involved are so unimaginably tiny that current technology falls far short of observing them directly. Even the most advanced particle accelerators, like the Large Hadron Collider, can't reach these dimensions. This leaves scientists in a challenging position. String theory's predictions are mathematically elegant and compelling, but without experimental evidence, they remain speculative. It's like trying to understand the depths of the ocean by only studying the waves on the surface. Another hurdle is the energy required to probe these scales. To observe quantum shadows or extra dimensions, we'd need energy levels far beyond what we can currently generate. It's as if we're trying to light up a vast, dark room with a single match. The light simply isn't strong enough to reveal what's hidden in the shadows. Despite these challenges, the pursuit of understanding quantum shadows through string theory continues to drive innovation and inspire new ways of thinking about the universe. These technological barriers don't diminish the importance of the questions being asked. In fact, they highlight just how mysterious and profound these realms are. As we push the boundaries of science, every failed experiment and every unanswered question brings us one step closer to unraveling the secrets of quantum shadows and the hidden dimensions they might inhabit. It's a journey filled with uncertainty, but also with the promise of discovery, a journey that could redefine our understanding of reality itself. Observing phenomena at scales smaller than the Planck length is like trying to read a book locked inside a vault with no key. Our current technology, as advanced as it seems, is simply not equipped to reach these unimaginably tiny distances. Take particle accelerators, for example. Machines like the Large Hadron Collider are marvels of engineering, capable of smashing particles together at incredible speeds to reveal the building blocks of matter. Yet even these massive devices fall far short of probing the Planck scale, which is about 10 to the power of 20 times smaller than a proton. It's not just a matter of building bigger or faster accelerators. The energy required to explore these distances exceeds anything humanity has ever produced. We're talking about energy levels so immense that they dwarf the capabilities of even our most ambitious projects. Microscopes, too, face insurmountable barriers. Electron microscopes can peer into the atomic world, revealing structures at the nanoscale, but they're nowhere near sensitive enough to detect fluctuations at the Planck length. Quantum mechanics itself introduces a fundamental constraint. The Heisenberg uncertainty principle tells us that measuring something so small would require such precision that it disrupts the very thing we're trying to observe. It's like trying to weigh a feather with a scale that's constantly shaking. These limitations aren't just technical, they're deeply rooted in the laws of physics as we understand them today. To bridge this gap, we'll need more than incremental improvements. We'll need revolutionary breakthroughs. Imagine inventing an entirely new kind of microscope, one that doesn't rely on light or electrons, but instead uses quantum entanglement to probe these hidden realms. Or perhaps we'll develop particle accelerators that harness energy in ways we haven't yet conceived, tapping into the quantum vacuum itself. The challenges are immense, but so are the rewards. Unveiling quantum shadows could reshape our understanding of reality, revealing new dimensions, particles, or even forces that we've never imagined. The question isn't just about building better tools, it's about rethinking how we approach the problem. Theoretical physicists are already exploring ideas like quantum gravity and holographic principles, seeking clues that might guide us toward the next leap in technology. Meanwhile, engineers and experimentalists are pushing the boundaries of what's possible, developing techniques like quantum sensing and ultra-precise measurements that inch us closer to this elusive frontier. It's a collaborative effort, one that requires creativity, persistence, and a willingness to challenge the status quo. As we stand on the edge of this uncharted territory, one thing is clear: exploring quantum shadows will demand not just new machines but a new way of thinking. It's a journey into the unknown, driven by curiosity and the relentless pursuit of knowledge. And while the path ahead is uncertain, the possibility of discovering something truly extraordinary makes it a journey worth taking. Theoretical proposals for observing quantum shadows are as bold and imaginative as they are ambitious. One promising avenue lies in quantum computing, which leverages the principles of superposition and entanglement to process information in ways classical computers cannot. Imagine a quantum computer so advanced it could simulate the behavior of particles at the Planck scale, offering a virtual window into this hidden realm. While current quantum systems are still in their infancy, the potential for breakthroughs in computational power could one day allow us to model the quantum shadows that evade direct observation. Gravitational wave detectors represent another fascinating frontier. These instruments, like LIGO and Virgo, have already transformed our understanding of the cosmos by detecting ripples in spacetime caused by cataclysmic events like black hole mergers. But what if we could enhance their sensitivity to detect gravitational waves from even smaller phenomena? Some theorists speculate that quantum fluctuations at the Planck scale might produce faint gravitational signatures, providing indirect evidence of the structures that lie beyond our current reach. This would be like listening for whispers in the universe's deepest silence, revealing secrets hidden in the fabric of spacetime itself. New types of particle accelerators are also being envisioned, ones that go beyond the brute force approach of smashing particles together. Concepts like plasma Wakefield accelerators promise to achieve higher energy levels in smaller spaces, potentially bringing us closer to the energy densities needed to probe the Planck scale. These innovations could open doors to discovering new particles or forces that govern the quantum shadows, reshaping our understanding of the fundamental laws of physics. The potential breakthroughs from these discoveries are staggering. Understanding quantum shadows could illuminate the origins of the universe, shedding light on the moments immediately after the Big Bang. It might reveal new dimensions of space or time, or even lead to the development of entirely new forms of energy, harnessing the quantum vacuum in ways we've never imagined. The implications extend far beyond technology, touching on the very nature of reality and our place within it. Philosophically, probing quantum shadows forces us to confront profound questions about the limits of human knowledge. What does it mean to explore realms that may inherently resist observation? Are there aspects of the universe that will forever remain beyond our grasp, or will our ingenuity and curiosity eventually unveil even the most elusive mysteries? These questions remind us that the pursuit of knowledge is not just about finding answers, it's about embracing the wonder of the unknown and the endless possibilities it holds. The existence of quantum shadows challenges not just our scientific understanding, but also our philosophical foundations. If reality has a smallest possible distance, a boundary beyond which we cannot probe, what does that mean for our perception of the universe? Are we, as conscious beings, inherently limited by the scale of our senses and instruments? These questions push us to reconsider the very nature of existence and the boundaries of knowledge. Quantum shadows might be more than just a technical hurdle. They could represent a fundamental limit to what we can ever know, forcing us to confront the possibility that some aspects of reality are forever hidden from us. This raises profound questions about consciousness itself. If our tools and senses are bound by scale, is our awareness similarly constrained? Philosophers have long debated the relationship between the observer and the observed, and quantum shadows add a new layer to that dialogue. If these phenomena exist beyond our reach, do they still shape reality in ways we cannot perceive, or do they exist in a realm entirely separate from our conscious experience? These ideas blur the line between the physical and the metaphysical, inviting us to think deeply about the interplay between the universe and the mind. What does it mean for reality to have a smallest possible distance? At first glance, it might seem like a technical detail, but it has far-reaching implications. If space itself is grainy at the Planck scale, then the smooth, continuous reality we perceive might be an illusion, a kind of cosmic approximation. This challenges our intuitive understanding of the world and suggests that our everyday experience is only a partial view of a much stranger, more intricate universe. It's like looking at a photograph and only seeing the pixels when you zoom in far enough, realizing that what seemed seamless is actually made of tiny, discrete elements. These ideas also resonate with broader questions about human curiosity and the pursuit of knowledge. Are there some truths that are simply beyond our grasp? If so, how should we approach them? Should we accept these limits or strive to push past them, even if success seems impossible? The concept of quantum shadows invites us to reflect on the nature of discovery itself, whether it's about finding definitive answers or embracing the beauty of the unknown. In a universe that may always hold secrets, the act of searching becomes just as meaningful as the answers we find. Quantum shadows might not just hint at the limits of our observable universe, they could also open a window into the multiverse. If these phenomena exist beyond the Planck length, they could potentially interact with other universes or dimensions, offering clues to a reality far larger than our own. Multiverse theory suggests that our universe is just one of many, each with its own physical laws and constants. Quantum shadows in this context might act as a kind of boundary or intersection point where the fabric of our reality brushes up against another. This idea bridges quantum mechanics and cosmology, suggesting that the smallest scales could hold the keys to understanding the vastness of existence. Scientists have long speculated that quantum fluctuations, tiny, unpredictable changes at the subatomic level, could be the seeds of alternate universes. If quantum shadows are a manifestation of these fluctuations at the Planck scale, they might provide indirect evidence for the multiverse. Imagine standing on the shore of an ocean where each wave represents a different universe. The foam at the edge of the waves, fleeting and almost invisible, could be likened to quantum shadows, the subtle, almost imperceptible interactions between realities. This analogy helps us visualize how these phenomena could serve as a bridge between worlds. The implications for our understanding of time are equally profound. If quantum shadows exist at the boundary between universes, they might also influence the flow of time itself. Time, as we experience it, might be just one dimension among many, with alternate timelines or realities coexisting alongside our own. Quantum mechanics already challenges our classical notions of time, with phenomena like entanglement suggesting that particles can influence each other instantaneously across vast distances. Quantum shadows could take this a step further, hinting at a deeper, more intricate structure of time that we have yet to fully grasp. These ideas push the boundaries of both science and imagination. They invite us to consider a universe or multiverse that is far more interconnected and complex than we ever imagined. While we may never directly observe these parallel realities, the study of quantum shadows could provide indirect evidence of their existence, reshaping our understanding of the cosmos. This exploration isn't just about answering questions, it's about discovering new ones, revealing the endless mysteries that lie beyond the smallest known distance. Time has always been one of the most elusive concepts in physics, but quantum shadows might hold the key to unlocking its deepest secrets. At scales smaller than the Planck length, time might not behave as we're used to. Instead of flowing in a straight line, it could twist, loop, or even fragment, creating possibilities that challenge our everyday experience. Theories suggest that at these infinitesimal scales, time could become entangled with space, blurring the line between the two and giving rise to phenomena like time loops. These loops could allow events to repeat themselves in ways that defy our classical understanding of cause and effect. Consider a river flowing steadily downstream, representing our familiar experience of time. Now imagine that somewhere in this river, tiny whirlpools form where the water circles back on itself. These whirlpools could be analogous to time loops at the quantum level, where moments repeat or overlap. Quantum shadows existing at this scale might be the markers of these loops, hinting at a reality where the past, present, and future are not as distinct as they seem. This could fundamentally change how we think about history, memory, and even free will. Quantum entanglement adds another layer to this mystery. When particles become entangled, their properties are linked no matter how far apart they are, and changes to one particle instantly affect the other. If time itself can become entangled at the quantum level, it could mean that events are connected in ways that transcend our linear perception. Picture a pair of clocks separated by vast distances, yet perfectly synchronized not through signals but through the very fabric of time. Quantum shadows might be the subtle imprints of these connections, offering clues to a deeper, more interconnected reality. These ideas don't just challenge our understanding of time, they could revolutionize it. If time loops or entangled timelines exist, the past, present, and future might not be fixed points but fluid, dynamic states. This could open the door to new ways of thinking about aging, causality, and even the nature of existence itself. While these concepts remain speculative, they push the boundaries of what we thought was possible, inviting us to explore a universe where time is far more intricate and mysterious than we ever imagined. Quantum shadows might hold the answer to one of the universe's most profound mysteries, dark matter. This invisible substance makes up about 85% of the universe's mass, yet it doesn't interact with light, making it impossible to detect directly with our current instruments. Its presence is inferred only through its gravitational effects, like bending light from distant stars or holding galaxies together. But what if dark matter's elusive nature is tied to phenomena occurring at scales smaller than the Planck length? Quantum shadows existing in this uncharted realm could provide the missing link. Imagine dark matter as a ghostly presence, hidden in plain sight, yet undetectable because it operates on a scale entirely different from the particles we're familiar with. At the quantum level, where distances become unimaginably small, particles might behave in ways that defy classical physics. Quantum shadows, as faint imprints of these behaviors, could represent the very particles that constitute dark matter. These particles might not emit or absorb light not because they're inert, but because they exist in a state that's fundamentally separate from the electromagnetic forces we rely on for observation. One compelling theory suggests that dark matter particles might interact through forces we haven't yet discovered, forces that only manifest at the quantum scale. Quantum shadows could be the echoes of these interactions, offering indirect evidence of their existence. For instance, if dark matter particles are influenced by a hidden dimension or a parallel quantum reality, their effects might only be detectable as subtle anomalies in the fabric of spacetime. Quantum shadows, then, could be the fingerprints of these elusive particles, hinting at a universe far more complex than we've imagined. The challenge lies in finding ways to observe these shadows. Current instruments are designed to detect particles and forces within the framework of known physics, but quantum shadows might require entirely new methods of detection. Advanced quantum sensors or experiments probing the Planck scale could one day reveal these shadows, shedding light on the nature of dark matter. Such discoveries wouldn't just solve a scientific mystery, they could redefine our understanding of the cosmos, opening the door to a universe where the unseen is as significant as the seen. Could quantum shadows be the key to unlocking the secrets of dark matter? While we don't yet have the tools to confirm this, the possibility is tantalizing. It invites us to rethink the boundaries of physics and explore a reality where the smallest scales hold answers to the biggest questions. As we continue to probe the quantum realm, we might just find that the shadows we've been chasing are the very essence of the universe's hidden structure. Detecting quantum shadows is no small feat. It's a task that pushes the boundaries of what's possible in experimental physics, requiring tools and techniques far beyond what we currently have. To observe phenomena at scales smaller than the Planck length, we'd need instruments of unimaginable precision. These devices would have to measure distances so tiny that they're almost beyond comprehension, and they'd need to do so without introducing any interference or error. The slightest imperfection in the equipment or the tiniest fluctuation in the environment could render the experiment useless. It's like trying to listen for a whisper in a hurricane. Every detail matters, and there's no room for mistakes. The energy requirements for such experiments are equally daunting. Probing the quantum realm at these scales demands levels of energy that are currently beyond our reach. Particle accelerators, the most powerful tools we have today, can't generate the necessary conditions to explore this frontier. We'd need entirely new technologies, perhaps even breakthroughs in energy production, to create the extreme environments required to glimpse quantum shadows. This isn't just about building bigger machines, it's about rethinking how we harness and apply energy in the first place. Data analysis presents another formidable challenge. The signals we're looking for would be incredibly faint, buried beneath layers of noise and interference. Detecting a quantum shadow would be like finding a single grain of sand on a vast, windswept beach. Current algorithms and computational methods aren't equipped to handle this level of complexity. We'd need to develop entirely new approaches to data analysis, combining advanced mathematics with cutting-edge artificial intelligence to sift through the noise and identify meaningful patterns. Even then, the process would be painstakingly slow, requiring vast amounts of computing power and time. These challenges make the search for quantum shadows one of the most ambitious endeavors in modern science. It's a quest that demands not only technological innovation, but also a fundamental shift in how we approach experimentation. Every step forward requires creativity, collaboration, and a willingness to explore uncharted territory. Yet, despite the difficulties, the potential rewards are immense. Discovering quantum shadows could revolutionize our understanding of the universe, revealing new layers of reality that have remained hidden until now. Mathematics plays a crucial role in this quest. It provides the language and tools needed to model the behavior of quantum shadows, even if we can't observe them directly. Through equations and theoretical frameworks, mathematicians and physicists can explore the implications of these phenomena, guiding experimentalists toward the most promising avenues of research. Without mathematics, the search for quantum shadows would be like navigating a dark labyrinth without a map, possible, but far more difficult and uncertain. Mathematics is the bridge that connects us to the unseen, a universal language that allows us to explore realities far beyond the reach of our senses. When it comes to quantum shadows, the role of mathematics becomes even more critical. These phenomena exist in a realm so small and so alien to our everyday experience that traditional observation simply isn't possible. Here, mathematics steps in as our guide, offering the tools to theorize, predict, and ultimately understand what lies beyond the Planck length. One of the most powerful frameworks for exploring quantum shadows is quantum field theory. This branch of physics uses mathematical equations to describe how particles and forces interact at the smallest scales. It's a way of mapping the unseen, providing a blueprint for how quantum shadows might behave. Through quantum field theory, physicists can model the fabric of space-time itself, probing the subtle ripples and fluctuations that hint at deeper layers of reality. It's like using a mathematical microscope, allowing us to zoom in on the tiniest details of the universe. Topology, another essential mathematical tool, offers a different perspective. While quantum field theory focuses on interactions, topology examines the shape and structure of space itself. It's the study of how space can twist, fold, or connect in ways that defy our everyday intuition. In the context of quantum shadows, topology helps us imagine how the universe might look at scales smaller than the Planck length. Could space be knotted or braided in ways we can't yet see? Topology provides the mathematical vocabulary to explore these possibilities, opening the door to entirely new ways of thinking about the cosmos. The beauty of mathematics lies in its ability to reveal connections that aren't immediately obvious. It's not just a tool for solving problems, but a way of uncovering patterns and relationships that might otherwise go unnoticed. For quantum shadows, this means finding links between seemingly unrelated phenomena, drawing parallels that illuminate the hidden structure of the universe. Mathematics allows us to see the big picture, even when the details remain elusive. But why is mathematics often the only way to explore these inaccessible realms? The answer lies in its abstract nature. Unlike experimental physics, which relies on tangible observations, mathematics operates in the realm of pure thought. It's unconstrained by the limitations of our physical tools, allowing us to explore ideas that might otherwise be impossible to test. This makes it uniquely suited to probing the quantum shadows, where traditional methods fall short. Through mathematics, we can venture into the unknown, guided by the power of logic and imagination. Quantum shadows may hold the key to one of the greatest mysteries in physics, the unification of general relativity and quantum mechanics. These two pillars of modern science describe the universe in fundamentally different ways. General relativity, Einstein's masterpiece, explains the behavior of gravity and the large-scale structure of the cosmos. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales. Yet, when it comes to understanding the universe at its most fundamental level, these two theories clash. At the Planck scale, where quantum shadows reside, the predictions of general relativity and quantum mechanics break down, leaving physicists with a puzzle that has yet to be solved. This is where quantum gravity comes into play. The quest for a theory of quantum gravity aims to bridge the gap between these seemingly incompatible frameworks. It's about finding a single, unified description that can explain both the curvature of space-time and the probabilistic nature of particles. Quantum shadows, as phenomena that emerge at this smallest of scales, could provide the clues needed to crack this mystery. They represent the point where the quantum and gravitational worlds intersect, offering a unique window into the deeper structure of reality. One of the most promising approaches to quantum gravity is string theory. This framework suggests that the fundamental building blocks of the universe are not point-like particles, but tiny, vibrating strings. These strings exist in higher dimensional spaces, and their vibrations give rise to all the particles and forces we observe. String theory naturally incorporates gravity, making it a strong candidate for unifying quantum mechanics and general relativity. Quantum shadows, in this context, could be seen as the echoes of these strings, the fleeting traces of their interactions in the fabric of space-time. Another compelling idea is loop quantum gravity, which reimagines space-time itself as a network of interconnected loops. In this theory, space isn't smooth and continuous but rather granular, made up of discrete units at the Planck scale. Quantum shadows could represent the transitions between these loops, the subtle shifts that define the geometry of the universe. By studying these shadows, physicists hope to uncover the underlying structure of space-time, revealing how gravity emerges from quantum processes. Why is this unification so crucial? Because without it, our understanding of the universe remains incomplete. General relativity and quantum mechanics each describe a different aspect of reality, but neither can fully explain the other. This creates a disconnect in our knowledge, leaving unanswered questions about the nature of black holes, the origins of the universe, and the behavior of matter and energy at the smallest scales. Quantum shadows, as phenomena that exist at the boundary between these two worlds, offer a unique opportunity to explore these questions. They could be the missing link that finally brings together the quantum and the gravitational, unlocking a deeper understanding of the cosmos. The implications of such a discovery would be profound. It could revolutionize our understanding of the universe, shedding light on everything from the Big Bang to the nature of dark matter and dark energy. It could also lead to new technologies inspired by the principles of quantum gravity that we can't yet imagine. For now, the search continues, driven by the hope that quantum shadows will illuminate the path to one of science's greatest achievements, a unified theory of everything. Black holes are often described as the ultimate cosmic mystery, but they might also hold the key to unraveling the secrets of quantum shadows. These enigmatic objects, where gravity becomes so intense that not even light can escape, create conditions that are unlike anything else in the universe. At the edge of a black hole, known as the event horizon, space and time are stretched and twisted in ways that challenge our understanding of physics. It's here, in this extreme environment, that the effects of quantum gravity may become detectable, offering a unique opportunity to study phenomena at scales smaller than the Planck length. Inside a black hole, all matter is crushed into an infinitely dense point called a singularity. According to general relativity, this singularity is where the laws of physics break down and quantum effects take over. But what happens at this point? Does space-time dissolve into a quantum foam, or do the rules of quantum mechanics somehow smooth out the singularity? These are questions that quantum gravity seeks to answer, and black holes provide a natural laboratory to explore them. The extreme conditions near a black hole could amplify the subtle effects of quantum shadows, making them observable in ways that would be impossible under normal circumstances. One of the most intriguing aspects of black holes is Hawking radiation, a theoretical prediction by physicist Stephen Hawking. According to this idea, black holes are not entirely black but emit a faint glow of particles due to quantum effects near the event horizon. This radiation carries information about the black hole's properties and could potentially reveal clues about the nature of quantum gravity. If quantum shadows exist, they might leave a detectable imprint in this radiation, providing a way to probe the smallest scales of the universe indirectly. Black holes also play a central role in the quest to unify quantum mechanics and general relativity because they embody the extremes of both theories. Their immense gravitational fields are described beautifully by general relativity, while their quantum properties, such as Hawking radiation, fall under the domain of quantum mechanics. By studying black holes, physicists hope to find a bridge between these two frameworks, uncovering how gravity emerges from quantum processes. Quantum shadows, as phenomena that exist at this interface, could be the missing piece of the puzzle, offering insights into how space-time behaves at the smallest scales. Imagine a black hole as a cosmic microscope, magnifying the subtle effects of quantum gravity that are otherwise invisible. Its immense gravitational pull distorts space-time in ways that could make quantum shadows detectable, even if indirectly. This makes black holes not just a fascinating astronomical phenomenon, but also a crucial tool in our quest to understand the fundamental nature of reality. By observing how black holes interact with their surroundings and emit radiation, we might uncover the hidden connections between quantum mechanics and gravity, bringing us closer to a unified theory of everything. The study of black holes and quantum shadows is a journey into the heart of the unknown, where the answers to some of the universe's deepest mysteries may finally be revealed. If quantum shadows exist beyond the Planck length, they could fundamentally reshape our understanding of information itself. Information theory, which explores how data is stored, processed, and transmitted, has become a cornerstone of modern physics, particularly in the study of black holes and quantum mechanics. At its core, this theory suggests that information is never truly lost, it can only be transformed or hidden. But what happens when we push this idea to the smallest conceivable scales? If quantum shadows represent fluctuations or structures at distances smaller than the Planck length, they might introduce a new layer to the nature of information, one that defies our current frameworks. Consider the concept of entropy, a measure of disorder or randomness in a system. In thermodynamics, entropy always increases, but in the quantum realm, it takes on a more nuanced role. Quantum systems can exhibit entanglement, where particles become interconnected in ways that defy classical logic. If quantum shadows exist, they could influence how entropy behaves at these infinitesimal scales, potentially revealing hidden patterns or connections that are currently beyond our detection. This raises profound questions. Could quantum shadows encode information in ways we don't yet understand? And if so, how would this affect our view of the universe as a computational system? The idea that information might be the fundamental building block of reality has gained traction in recent years. Some physicists propose that space-time itself emerges from a vast network of quantum bits or qubits interacting in complex ways. If this is true, then quantum shadows could represent the fine-grained details of this underlying information network. They might be the threads that weave the fabric of reality, operating at scales so small that they blur the line between existence and abstraction. This perspective shifts the focus from matter and energy to patterns and relationships, suggesting that the universe is, at its heart, a vast information processing system. But how do quantum shadows fit into this framework? If they exist, they could challenge the limits of computation by introducing new rules or constraints at the smallest scales. For instance, if information is encoded in quantum shadows, it might require entirely new methods to decode or interpret. This could lead to breakthroughs in fields like quantum computing, where the manipulation of information at the subatomic level is already pushing the boundaries of what's possible. At the same time, it might force us to reconsider the very nature of reality, asking whether what we perceive as physical objects are, in fact, manifestations of deeper informational structures. Exploring the connection between quantum shadows and information theory invites us to rethink some of the most fundamental questions in physics. Is information the true currency of the universe? And if so, how do phenomena at the Planck scale and beyond influence its flow and transformation? The answers to these questions could not only deepen our understanding of quantum gravity, but also open new doors to the nature of existence itself. By peering into the quantum shadows, we might uncover the hidden language of the cosmos, written in the smallest strokes of information imaginable. Quantum shadows could hold the key to one of the most profound questions in science and philosophy. What is the true nature of reality? For centuries, humans have grappled with the idea of what lies beneath the surface of the world we perceive. Some of the most intriguing theories in modern physics suggest that reality might not be as solid and concrete as it seems. The holographic principle, for example, proposes that our three-dimensional universe might be a projection of information encoded on a two-dimensional surface. Imagine a hologram where a flat, seemingly simple surface contains all the data needed to create a fully immersive, three-dimensional image. If this principle holds true, quantum shadows could represent the underlying code of this cosmic hologram, the intricate patterns of information that give rise to the universe as we know it. Another perspective comes from the simulation hypothesis, which suggests that our reality might be an advanced digital construct, akin to a highly sophisticated computer program. In this view, quantum shadows could be the algorithms or data points that form the foundation of this simulation. Just as a video game relies on lines of code to create a virtual world, the universe might be built on an unseen layer of quantum interactions. This idea blurs the line between science and philosophy, raising questions about the nature of existence itself. Are we living in a simulated reality? And if so, what does that mean for our understanding of free will, consciousness, and the purpose of life? These theories have far-reaching implications, not just for physics but for how we approach science as a whole. If quantum shadows are the building blocks of reality, then studying them could unlock new ways to manipulate the fundamental aspects of existence. For example, understanding the holographic principle might lead to breakthroughs in quantum computing, enabling us to process information in ways that are currently unimaginable. Similarly, the simulation hypothesis could inspire new approaches to artificial intelligence and virtual reality, pushing the boundaries of what we can create and experience. On a philosophical level, these ideas challenge our assumptions about the nature of existence. If reality is a projection or a simulation, what does that say about the concept of truth? Could our perceptions be fundamentally different from the underlying reality? These questions force us to reconsider the very foundations of knowledge and perception, inviting us to explore the boundaries between science, philosophy, and even spirituality. In everyday life, the implications of quantum shadows and their role in shaping reality might seem abstract, but they could influence how we think about technology, creativity, and even our place in the universe. If the world around us is built on a foundation of information, then understanding quantum shadows could help us harness that information in new and innovative ways. From developing advanced technologies to reimagining our relationship with the cosmos, the study of quantum shadows offers a glimpse into a future where the boundaries between the physical and the informational are blurred, opening up a world of possibilities that we are only beginning to explore. The search for patterns in the quantum realm is like piecing together an infinite puzzle, where every fragment holds the potential to reveal the hidden architecture of the universe. Physicists scrutinize the behavior of particles at the smallest scales, looking for recurring symmetries and relationships that might point to deeper truths. These patterns are not just random coincidences, they could be the fingerprints of quantum shadows, the subtle imprints of something far more fundamental at work. For instance, the mathematical elegance of equations like those in string theory or quantum field theory often hints at underlying principles that govern the behavior of particles and forces. These frameworks suggest that the chaos of the quantum world might be a reflection of a hidden order waiting to be decoded. One striking example of this search is the study of quantum entanglement, where particles become so deeply connected that their properties are instantly correlated, no matter the distance between them. This phenomenon, which Albert Einstein famously called spooky action at a distance, challenges our understanding of space and time. Yet, it also hints at a deeper layer of reality, where the apparent separateness of objects might be an illusion. Could quantum shadows be the bridge that links these entangled particles, facilitating their mysterious connection? The idea is as tantalizing as it is elusive, pushing scientists to explore even more exotic concepts like wormholes or higher dimensional spaces. Imagination plays a crucial role in this quest, as physicists must often think beyond the confines of known physics to uncover these patterns. The history of science is filled with examples where creativity led to groundbreaking discoveries. Consider how James Clerk Maxwell's imaginative unification of electricity and magnetism laid the foundation for modern physics. Today, researchers face a similar challenge, using thought experiments and theoretical models to envision what lies beyond the smallest known distances. These mental explorations are not flights of fancy but essential tools for navigating the uncharted territories of the quantum world. The search for patterns is also a reminder that science is as much an art as it is a discipline. Just as an artist sees the world in shapes and colors, a physicist sees it in symmetries and equations. Both are driven by a desire to uncover the hidden beauty of reality, to find the connections that make the universe feel coherent and meaningful. In this way, the study of quantum shadows is not just a scientific endeavor but a deeply human one, reflecting our innate curiosity and the endless quest to understand the world around us. The power of imagination in physics cannot be overstated. It's the spark that ignites the flame of discovery, allowing us to venture beyond the boundaries of what we know and into the uncharted territories of the quantum realm. Think about how Niels Bohr's imaginative leap led to the development of quantum mechanics, or how Albert Einstein's thought experiments reshaped our understanding of space and time. These breakthroughs didn't come from rote memorization or rigid formulas, but from daring to imagine the impossible. Quantum shadows, the elusive patterns that might lie beyond the smallest known distances, demand that same kind of creative thinking. They challenge us to question our assumptions and to see the universe not just as it is, but as it could be. Imagination in science is not just about dreaming up wild ideas. It's about finding the courage to explore the unknown. Consider string theory, which proposes that the fundamental particles we observe are actually tiny, vibrating strings. This idea emerged from a willingness to think beyond the traditional framework of particles and waves, to envision a reality that's far more complex and interconnected. Similarly, the concept of the multiverse, the idea that our universe might be just one of many, pushes the boundaries of what we consider possible. These theories are not just intellectual exercises, they're attempts to uncover the deeper truths that quantum shadows might be hinting at. Embracing curiosity and wonder is essential for this kind of exploration. It's what drives scientists to ask the big questions. What lies beyond the smallest known distances? How do particles communicate across vast stretches of space? What hidden connections might exist that we haven't yet imagined? These questions don't have easy answers, but they inspire us to keep searching, to keep pushing the limits of our understanding. And it's not just scientists who can engage in this kind of thinking. Anyone with a curious mind can ponder these mysteries, using their imagination to explore the possibilities. The history of science is filled with examples of how imagination has led to revolutionary ideas. Take the work of Richard Feynman, whose playful, intuitive approach to physics helped uncover new insights into quantum electrodynamics. Or consider the story of Marie Curie, whose relentless curiosity drove her to discover radioactivity, opening up entirely new fields of research. These pioneers remind us that imagination is not just a tool for artists and writers, it's a vital part of scientific discovery. By encouraging us to think beyond the conventional, to question the status quo, and to embrace the unknown, imagination helps us uncover the hidden truths of the universe. So, as we ponder the mysteries of quantum shadows, let's remember the power of imagination. It's the key that unlocks the door to new discoveries, the bridge that connects the known to the unknown. Whether you're a scientist, a student, or simply someone who loves to wonder about the mysteries of the universe, don't be afraid to let your imagination roam free. After all, the next groundbreaking idea might be just one imaginative leap away. Quantum shadows invite us to consider one of the most profound mysteries of all consciousness. What if the strange, unpredictable behavior of particles at the smallest scales is somehow linked to the way our minds work? This idea might sound like science fiction, but some scientists and philosophers have begun to explore the possibility that quantum phenomena could play a role in the workings of consciousness. Could it be that the same forces shaping the quantum realm are also shaping our thoughts, our awareness, and our sense of self? One of the most intriguing theories in this area comes from physicist Roger Penrose and anesthesiologist Stuart Hameroff. They proposed that microtubules, tiny structures within our brain cells, might function as quantum computers, processing information in ways that classical physics cannot explain. This theory, known as OR, suggests that consciousness arises from quantum processes happening at an incredibly small scale. While this idea is still highly debated, it opens the door to a fascinating question. Could our minds be tapping into the same quantum shadows that physicists are trying to understand? This connection could have profound implications for how we see ourselves and the universe. If consciousness is rooted in the quantum realm, it might mean that our thoughts and perceptions are not just passive observations but active participants in shaping reality. This idea echoes the principles of quantum mechanics, where the act of observation can influence the outcome of an experiment. Could our awareness be a kind of quantum interaction, weaving itself into the fabric of the cosmos? Exploring this possibility also raises questions about the nature of free will. If our decisions are influenced by quantum processes, does that mean they're governed by randomness? Or could there be a deeper order within the chaos, one that allows for genuine choice and creativity? These questions challenge us to rethink not just the mind but the very foundation of reality. While these ideas are speculative, they highlight the incredible complexity of both the quantum world and the human mind. Whether or not quantum shadows hold the key to consciousness, the exploration itself is a testament to our endless curiosity and desire to understand the mysteries of existence. It reminds us that the universe is full of surprises and that the smallest distances might be hiding some of the biggest truths. Quantum shadows not only challenge our understanding of the universe, but also hold the potential to reshape the future of technology in ways we can scarcely imagine. At the heart of this transformation is quantum computing, a field that directly leverages the strange behavior of particles at the smallest scales. Traditional computers rely on bits, which can be either 0 or 1. Quantum computers, however, use qubits that can exist in multiple states simultaneously, thanks to a phenomenon called superposition. This allows quantum computers to process vast amounts of information at once, potentially solving problems that would take classical computers millions of years to crack. From designing new medicines to optimizing global logistics, the applications are staggering. Energy production could also see a quantum leap, literally. Imagine harnessing the power of quantum tunneling, where particles pass through barriers that should be impenetrable. This principle could lead to breakthroughs in fusion energy, offering a virtually limitless and clean power source. By understanding how particles behave at these minuscule distances, scientists might unlock new ways to control and stabilize plasma, the superheated state of matter needed for fusion. The result, a future where energy scarcity becomes a thing of the past. Space travel could be another frontier transformed by quantum shadows. The extreme precision required to navigate the cosmos might benefit from quantum sensors, which can measure gravitational waves and other phenomena with incredible accuracy. These sensors could guide spacecraft through the vast emptiness of space, avoiding collisions and enabling pinpoint landings on distant planets. Even the concept of propulsion could be revolutionized. Theoretical ideas like the Alcubierre drive, which involves bending spacetime itself, might become feasible if we can manipulate quantum fields on a fundamental level. What makes these possibilities so exciting is the way they connect the smallest scales to the grandest ambitions. The same principles that govern particles smaller than atoms could one day redefine how we travel, power our world, and solve humanity's greatest challenges. By peering into the quantum shadows, we're not just uncovering the secrets of the universe, we're unlocking the tools to shape it. The pursuit of knowledge beyond the Planck length raises profound ethical questions that demand careful consideration. As we venture into these uncharted territories, we must ask ourselves not just what we can discover, but what we should discover. The ability to manipulate phenomena at such infinitesimal scales could lead to groundbreaking technologies, medical advancements, energy solutions, and computing power that redefine human capabilities. Yet, with such power comes the responsibility to ensure these discoveries are used for the benefit of all, not just a privileged few. The potential for misuse is significant. For instance, quantum technologies could revolutionize communication, but they might also enable unprecedented levels of surveillance or cyber warfare. The ethical implications extend beyond technology. If probing the Planck length reveals new dimensions or fundamentally alters our understanding of space, time, and reality, how do we prepare society for such paradigm shifts? These discoveries could challenge long-held beliefs, spark philosophical debates, and even reshape cultural and religious frameworks. It's crucial to engage diverse voices in these discussions: scientists, ethicists, policymakers, and the public, to ensure that the fruits of this exploration are harnessed wisely. We must also consider the environmental and societal impacts. The energy and resources required for such advanced research could be immense, and we must weigh the benefits against the costs. Are we prioritizing the right questions, or are we risking harm in the name of progress? Ultimately, the exploration of quantum shadows is not just a scientific endeavor, it's a deeply human one. It compels us to reflect on our values, our priorities, and our shared future. As we stand on the brink of these discoveries, let us strive to approach them with curiosity, humility, and a commitment to the greater good. The journey into the unknown is thrilling, but it is our collective responsibility to ensure that it also brings light, not shadows. The search for extraterrestrial life has always been one of humanity's most tantalizing quests. But what if the answers lie not in distant stars or planets, but in the quantum shadows that hide beyond the smallest known distance? At scales smaller than the Planck length, the fabric of reality behaves in ways that defy our everyday understanding. These quantum phenomena could hold clues to the very building blocks of life itself. For instance, if life arose from the intricate interplay of particles at these minuscule scales, then understanding quantum shadows might reveal universal principles governing biology across the cosmos. Imagine a scenario where alien life forms evolved to harness quantum effects in ways we can scarcely comprehend. Their intelligence might not rely on traditional chemistry or biology as we know it, but could instead be rooted in manipulating quantum states or even existing in dimensions beyond our perception. This raises the possibility that signs of extraterrestrial life might not be found in radio signals or atmospheric gases, but in subtle anomalies at the quantum level. Scientists have already speculated that quantum entanglement, a phenomenon where particles remain connected across vast distances, could be used for faster-than-light communication. Could advanced civilizations be using similar principles to communicate or even travel across the universe? Furthermore, the conditions necessary for life might be influenced by quantum phenomena. For example, quantum fluctuations could play a role in the formation of stars, planets, and even the complex molecules that give rise to life. If quantum shadows shape the fundamental forces of nature, then understanding them could help us identify the most likely places to find life in the universe. This leads us to a profound question. Could quantum shadows hold the key to finding life beyond Earth? As we peer into these infinitesimal realms, we might not only uncover the secrets of the universe, but also discover that life, in all its forms, is far more interconnected and universal than we ever imagined. The journey into the quantum shadows isn't just about exploring the smallest scales. It's about expanding our understanding of life itself, both here and among the stars. Quantum shadows, those elusive phenomena that operate beyond the smallest known distance, might hold the key to understanding not just life but the very origins of the universe itself. At scales smaller than the Planck length, the rules of classical physics dissolve, giving way to a realm governed by quantum mechanics. Here, scientists speculate that the seeds of the Big Bang could have been planted. The universe, in its earliest moments, was unimaginably tiny, so small that quantum effects would have dominated its behavior. This raises the possibility that quantum shadows played a crucial role in the rapid expansion known as cosmic inflation. During this period, the universe expanded faster than the speed of light, stretching from a microscopic speck to the vast cosmos we see today. But what powered this expansion? Some theories suggest that quantum fluctuations, tiny ripples in the fabric of space-time at these minuscule scales, could have been the driving force. These fluctuations, amplified by inflation, might have laid the groundwork for the large-scale structures we observe, such as galaxies and galaxy clusters. Beyond inflation, quantum shadows could also explain the fundamental forces of nature. Gravity, electromagnetism, and the strong and weak nuclear forces all emerge from interactions at the quantum level. Understanding these forces in their most basic form could reveal why the universe behaves the way it does. For instance, why is gravity so much weaker than the other forces? Could quantum shadows offer an explanation hidden in the interactions at the Planck scale? This knowledge isn't just academic, it's essential for understanding our place in the cosmos. By exploring the quantum shadows, we're not only peering into the origins of the universe, but also uncovering the mechanisms that shape its evolution. This journey into the quantum realm could redefine our understanding of reality, offering insights into the forces that govern everything from the smallest particles to the largest structures in the universe. As we delve deeper, we might find that the answers to the universe's greatest mysteries lie in the shadows of the quantum world, waiting to be illuminated by the light of discovery. The quest to uncover the secrets of quantum shadows isn't a solitary endeavor. It's a collaborative effort that brings together minds from across the scientific spectrum. Physicists, mathematicians, and engineers each play a vital role in this exploration, contributing unique perspectives and expertise. Physicists delve into the theoretical frameworks, crafting hypotheses about how quantum shadows operate at the smallest scales. Mathematicians develop the complex equations needed to model these phenomena, translating abstract ideas into tangible predictions. Engineers, on the other hand, design the cutting-edge instruments required to test these theories, pushing the boundaries of technology to measure the immeasurable. This interdisciplinary approach is essential because the challenges at the frontier of science are too vast for any single field to tackle alone. Quantum shadows exist at the intersection of multiple disciplines, requiring a synthesis of knowledge to fully understand their nature. Collaboration fosters innovation, allowing scientists to pool their strengths and overcome obstacles that might seem insurmountable in isolation. But the journey doesn't end in the lab or the lecture hall. Public engagement plays a crucial role in advancing scientific discovery. By sharing their work with the broader community, scientists can inspire curiosity, foster a deeper appreciation for the natural world, and even attract the next generation of researchers. Public support also helps secure the funding and resources needed to continue these groundbreaking investigations. The story of quantum shadows isn't just about particles and equations. It's about people, scientists, engineers, educators, and curious minds everywhere coming together to unravel the mysteries of the universe. This collective effort reminds us that the pursuit of knowledge is a shared human endeavor, one that has the power to transform our understanding of reality and our place within it. Engaging the public in the search for quantum shadows is more than just a way to share scientific discoveries. It's a bridge that connects the complexities of science with everyday curiosity. Science communication transforms abstract concepts into stories that resonate, sparking wonder and inspiring questions about the universe. When scientists take the time to explain their work in accessible ways, they're not just sharing information, they're inviting people to join in the journey of discovery. This dialogue creates a space where creativity thrives, as diverse perspectives and ideas can lead to breakthroughs that might not emerge in a closed research environment. Public engagement also plays a crucial role in building support for scientific endeavors. Groundbreaking research often requires significant resources, funding, infrastructure, and collaborative networks. When the public understands the value and excitement of exploring quantum shadows, they're more likely to advocate for the investments needed to push these investigations forward. But the benefits go beyond funding. Sharing the story of quantum shadows can ignite a passion for science in young minds, encouraging the next generation of physicists, engineers, and innovators. It's a chance to show that science isn't just about equations and experiments. It's about curiosity, imagination, and the thrill of uncovering the unknown. This connection fosters a sense of community where everyone, regardless of their background, can feel a part of something extraordinary. So, as we continue to explore the mysteries of quantum shadows, let's remember the power of sharing our discoveries. Whether it's through videos, articles, or conversations, every effort to communicate science helps to build a world that values curiosity and innovation. And to you, the viewer, we invite you to be a part of this journey. Share your thoughts, ask questions, and let's explore these ideas together. Because in the end, science is not just for scientists, it's for all of us. Quantum shadows challenge not just the limits of our technology, but the very boundaries of human understanding. They might represent a frontier where the universe itself sets the rules, and our ability to perceive or measure hits a fundamental wall. This raises a profound philosophical question. Are there aspects of reality that will forever remain hidden from us, no matter how advanced our tools or theories become? Throughout history, humans have pushed the boundaries of knowledge, from the depths of the oceans to the vastness of space. Yet, at the quantum level, the rules seem to defy our intuition. Heisenberg's uncertainty principle, for instance, tells us there are intrinsic limits to what we can know about particles. Quantum shadows might be an extension of this idea, a reminder that the universe doesn't always bend to our desire for clarity. This isn't just a scientific challenge, it's a deeply human one. The pursuit of knowledge is driven by curiosity, but what happens when we confront questions that have no answers? Some might see this as discouraging, but others find it exhilarating. After all, it's the unknown that fuels discovery. Think of quantum shadows as cosmic puzzles waiting to be solved, or perhaps as eternal mysteries that keep us humble. They remind us that the universe is vast, complex, and often enigmatic. And while we may never fully unravel these shadows, the act of searching itself is a testament to human ingenuity and resilience. It's a journey that invites us to ask better questions, to refine our methods, and to embrace the wonder of not knowing. So, as we peer into the quantum realm, let's not just seek answers. Let's celebrate the questions that remind us how much there is still to explore. The beauty of the unknown lies in its ability to spark wonder and ignite the imagination. Quantum shadows, with their elusive nature, remind us that the universe is not just a collection of facts to be catalogued, but a tapestry of mysteries waiting to be explored. This search for understanding is not just a scientific endeavor, it's a deeply human one. It's the same drive that led ancient civilizations to map the stars, that inspired poets to write about the cosmos, and that pushes artists to capture the infinite in their work. Consider how the mysteries of the quantum realm have influenced literature, from the surreal landscapes of science fiction to the thought-provoking musings of philosophical essays. They've inspired composers to create music that echoes the ethereal nature of particles and painters to depict the unseen forces that shape reality. These creative expressions are more than just reflections of science, they're testaments to the human spirit's boundless curiosity. Quantum shadows also challenge us to think beyond the tangible, urging us to consider questions that have no easy answers. What is the nature of reality? Are there dimensions beyond our perception? These inquiries might seem abstract, but they resonate deeply with our innate desire to make sense of the world. They remind us that the pursuit of knowledge is not just about finding answers, it's about embracing the journey itself. In a world that often values certainty, the unknown offers a refreshing reminder that there is still so much to discover. It invites us to stay curious, to keep asking questions, and to find beauty in the gaps of our understanding. As we stand on the edge of the quantum frontier, let's not just marvel at what we've learned. Let's celebrate what we've yet to uncover, knowing that every mystery we encounter is a gateway to new possibilities. The shadows may hide answers, but they also illuminate the path forward, a path paved with wonder, creativity, and the unyielding spirit of exploration. From the Planck length to the enigmatic quantum shadows, we've ventured into the realm where the familiar rules of physics dissolve into a sea of uncertainty. This journey reminds us that the universe is far stranger and more intricate than we often imagine. The Planck length, the smallest known distance, serves as a boundary beyond which our current understanding falters, yet it's also a doorway to the profound mysteries of quantum shadows, those elusive phenomena that hint at the deeper structure of reality. These ideas aren't just abstract concepts, they challenge us to rethink our place in the cosmos. They remind us that every discovery, no matter how small, is a step toward unraveling the grand tapestry of existence. As we ponder these mysteries, we're reminded of the words of physicist Richard Feynman. Nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. This quest for understanding is not just about finding answers, it's about embracing the beauty of the unknown and the thrill of exploration. So, as we close this chapter, let's carry this spirit of curiosity forward. Subscribe to continue this journey, share your thoughts with fellow explorers, and never stop asking questions. The universe is vast, and its mysteries are infinite, but so too is our capacity to wonder, to learn, and to dream. The adventure is just beginning.